Hello, my name is Matthew Bell, and this is a presentation on our research to design and implement the first fiber-reinforced polymer wildlife overpass in North America. Fiber-reinforced polymers, or FRPs, is a relatively new material and has only been used in infrastructure projects for a few decades. First, we had to do a literature review to understand the limits and strengths of FRP and how they are used in infrastructure projects. This process involves communicating with manufacturers in North America and Europe to identify if they are able to build a large overpass structure. We then took that knowledge that we gained and created preliminary designs for an FRP overpass with Department of Transportation input. The goal was to design an overpass that can be built in the US with minimal departure from the DOT standard approval processes. We then took the preliminary designs and compared the life cycle costs of FRP to traditional materials used in wildlife mitigation. FRPs are a composite material of structural fibers set in a mold of thermoset resin. Thermoset resins do not get soft at elevated temperatures, so they restrain the fibers against buckling to allow the transfer of shear stress between them. This results in a very strong and very light composite material. The average FRP bridge is half the weight of a steel bridge with the same strength, and it is 5 times lighter than its concrete equivalent. Depending on the properties of the resins and fibers used within FRP structures, they can resist environmental corrosion, rot, and water absorption, and they can also be fire, UV, and impact resistant. Virgin materials are currently the most durable, but research suggests bio-based and recycled materials will be more commonly used in the future. FRP structures generally follow the principles of accelerated bridge construction techniques, but the lightweight characteristics of FRP also helps reduce the transportation and construction costs. Trucks are able to carry more elements on one load, and smaller cranes can be used to hoist them into position. The characteristics of FRP composites results in a long-lasting structure that requires little to no maintenance over its 100-year service life. There are two main manufacturing processes that are applicable to FRP infrastructure. The first is pultrusion molding. This is the process where the fibers and resin are pulled through a mold simultaneously to create continuous members that can be cut to any length. It is an intensive process, but extremely efficient when large quantities of a standard section are needed. The second method is vacuum infusion. This process pumps resin through a custom-shaped mold with the desired fiber layout. This manufacturing process is used to create custom molded shapes and can integrate other materials into the mold to reduce weight, increase strength, and/or reduce the amount of resin required. The dimensional constraints of FRP products are limited by transportation and logistics, not in the structural properties and technology itself. In theory, there is no limit to the dimensions of an FRP element in a bridge design. There are three types of FRP bridges, each having their own benefits and limitations for design and construction. The first is pultrusion-style bridges. These bridges are constructed using FRP members using steel and lumber construction techniques and are commonly connected with stainless steel hardware. Here are two images of innovative pultrusion bridges. The top image is the longest FRP pultruded clear span bridge in the world being installed in Bermuda. The bridge is 46 meters long and 2.5 meters wide. The FRP bridge was selected for this location for its ability to resist the alkaline atmosphere along the coast. The bottom image shows the longest bridge in the world made from recycled plastic. It is 27 meters long, it can support 97,000-pound traffic loads, and it is made of over 110,000 pounds of waste plastic. The second type of structure are FRP hybrid bridges. These bridges integrate FRP composites with other structural materials like concrete and steel. They are currently the most widely used FRP bridge system because they combine the benefits of FRP with the familiarity and experience that exists with more traditional materials. The top left image is a 22-meter hybrid vehicle bridge over the B3 highway in Germany. It utilizes an FRP deck on top of steel girders. Connecting the deck beforehand allowed the entire structure to be created at one time. The bottom left image is a 140-meter pedestrian bridge over the A27 highway in the Netherlands. This viaduct used a steel support frame for the span with FRP decking. The lightweight decks allowed them to be connected to the steel frame prior to installation, and then the entire structure was maneuvered into place. The two images on the right are of the 16-meter fish passage under State Road 203 in Washington. This hybrid system uses concrete-filled FRP tubes with FRP paneling to create the superstructure. Commercial champions of this technique claim a bridge span can be completed in as little as 3 days. The third type of FRP structures are unimold bridges. These bridges are created with a single vacuum infusion process to make one large bridge structure as a single unit. They may incorporate other materials within the mold, but are only to fill voids and do not rely on the strength of the material fillers like the hybrid bridges do with concrete and steel. Unimold bridges reduce the amount of non-FRP hardware and connections required to build and install the bridge. In the top left image, you can see an entire 36-meter unimold bridge being lifted into place. The bottom left image is a 54-meter arched pedestrian bridge in the Netherlands. This bridge connects two nature areas near the city and has enough clearance to allow boats to pass underneath. The top right image is a 27-meter pedestrian bridge along a hiking path in Poland. And the bottom right image is an ecoduct in the Netherlands and was the first FRP wildlife overpass ever created. Now that we have a general understanding of the properties of FRP composites and their applications for bridge construction, we move on to our design of a wildlife crossing overpass. The design goal was to work on a real-world mitigation site to evaluate the steps and hurdles required to implement an FRP wildlife overpass in the US, with the hope that the DOT will continue to work and build the structure. This image is an example of an innovative FRP and wood core structure created for a wildlife crossing design challenge hosted by ARC Solutions. The sites proposed by our technical advisory committee were evaluated based on local and regional conservation value, wildlife vehicle collision mortality, road barrier effects, land use security, and mitigation options. The selected mitigation site was a 12-mile section of US 97 in Siskiyou County, California. This site has been identified as both a barrier and safety concern by Caltrans and the California Department of Fish and Wildlife. It is an essential connectivity area and in the top 5% for deer vehicle collision density in California. Collared elk data has revealed there are multiple locations where elk approach the roadway but are hesitant to cross, which are represented by the black dots in the right image. During the summer of 2020, the WTI team traveled to California to visit with members of Caltrans, California Department of Fish and Wildlife, U.S. Forest Service, and other local stakeholders. Together, we evaluated the section of road and potential crossing locations. The wildlife overpass design site was chosen based on safety, conservation, bridge design options, and management criteria. The site selected for our wildlife overpass design was located at the Grass Lake Summit, indicated here by the red arrow. This site is on a ridgeline just over 5,000 feet in elevation. It is a seasonal migration route for deer and elk, and there are high rates of vehicle collisions with these species at this location. The Grass Lake Summit is a below-grade, 3-lane section of highway, making it ideal for an overpass because it will reduce the amount of fill dirt required for approach ramps. A preliminary layout was provided by Caltrans that indicated specific bridge requirements, like abutment type, vehicle clearance, and the span of the bridge. It also included estimated fencing, jump outs, and road access points along the adjacent mitigation area. We used this as the starting point of our designs and communicated with Caltrans engineers, project managers, and maintenance staff along the way to ensure concerns and ideas were being addressed by everyone involved in the design and long-term maintenance of the structure. After evaluating the FRP bridge manufacturers, we decided that Advanced Infrastructure Technologies is the best manufacturer moving forward. AIT's new composite bridge system is a long-life solution to traditional steel and concrete deck bridges. The system consists of lightweight FRP tub girders that are simply supported on standard foundations with precast panels or cast-in-place concrete bridge decks. The FRP tub girder system was reviewed by bridge engineers and maintenance workers on our Caltrans committee, and it was agreed that the AIT tub girders created the lowest risk for the FRP wildlife overpass approval process and maintenance inspections. ARC Solutions and WTI hosted an interdisciplinary team of experts to evaluate the use of FRP materials into the structural and ecological designs of wildlife crossings. There was representation from 11 state and federal agencies in the US and Canada. The design lab was divided into landscaping and engineering sessions that evaluated applications of FRP to the US 97 structural designs and for wildlife crossings in general. Using a virtual design format allowed us to work simultaneously on the same page and interact in a way that resembled in-person meetings. The landscaping working sessions evaluated different aspects of wildlife crossings, including the species present at the mitigation site and the amount of landscaping that should be applied to the top of the structure. We looked at all the benefits and challenges of minimal landscape to fully forested structures. The landscaping is an important part of wildlife crossing structures because it helps to create functional crossings that are appealing to the target species and are used to determine the loads required for the superstructure. The engineering portion of the design lab focused on the current and potential applications of FRP to wildlife crossings. The results were organized into 3 categories: basic, enhanced, and innovative. The basic category includes FRP elements that are developed, tested, and can be implemented along North American road networks. There are readily available technologies that use conventional construction methods and require minimal departure from existing agency practices. The enhanced category includes modifications to the wildlife crossing designs that provide opportunities to integrate FRP in novel ways that leverage and demonstrate the material's positive qualities, enhance the ecological and structural function of the crossing, or provide benefits in the form of interpretive components. These applications may require additional agency approval or veer from traditional construction methods. Applications in this category include the use of FRP fence posts and barriers, FRP rebar and lightweight concretes, and the use of recycled plastic FRP for non-structural elements. The innovative category requires additional research prior to their integration into a wildlife crossing design and need further investigation based on their potential to deliver benefits in structural design, feasibility, sustainability, or ecological function. All the ideas derived from the virtual design lab were evaluated for their applications for the bridge superstructure along US 97. With the target species being elk and deer, it is recommended that the crossing structure be 50 meters wide. This will allow ample space and provide an area of the landscaping for elk to have a clear line of sight across the overpass. Other dense pathways and islands are created for deer and other species that like to have more cover within the landscape. Approximately 75 centimeters of soil should be applied to accommodate low-growing shrubs and other native plant species locally sourced from the surrounding area. The geometry and landscaping of the overpass were used to determine the loads required for the structure, and AIT provided preliminary cross-section measurements for the composite tub girder. This schematic shows a cross-section of the FRP bridge design. 2 composite tub girders are connected with a precast concrete panel, so 2 girders can be lifted into place at once. After all the girders are in place, high-strength concrete closure joints connect all the precast concrete, and the remaining concrete deck is poured into place. This method reduces construction time of placing the girders and removes the need to build framework for the concrete deck. A concrete curb is used to retain the perforated drain pipe, coarse aggregate, and soil. A sound and light barrier is mounted to the top of the curb to reduce visibility of the passing vehicles. The goal was to use as much FRP material as possible. In addition to AIT tub girders, we recommend the use of lightweight concrete mixes and/or FRP rebar in bridge deck and abutments. For non-structural elements, including sound and light barriers, fence posts, and wildlife jump outs, recycled plastic FRP is an applicable solution for the long-term goals of the US 97 mitigation site. Because this is a new approach to wildlife crossings, we are being conservative on our designs. It needs to be innovative, but not too extreme that the bridge will not be approved. We are setting the stage for FRP wildlife crossings and hope to inspire more creative and sustainable methods for the future. The last section of this project aims to compare the life cycle cost of FRP to traditional materials commonly used. For this, we focused on the specific material applications and left all other comparisons as equal, which means we excluded the social and environmental costs. This LCC uses a 2.5% discount rate for future costs over the 100-year analysis and uses the estimated US dollar value from 2019. The image on the right shows the mitigation layout with all associated elements used in this analysis. These are some of the assumptions made for the superstructure analysis. It only compares the difference in girder type and assumes all other aspects of the bridge are equal, meaning this analysis includes girder manufacturing, transportation, construction, and maintenance over 100 years. Some people will argue that wildlife crossings will have a longer service life than transportation bridges, but the reality is that we do not have the information to support this because they are a relatively new structure type and none have made it to the end of service date. Therefore, we went with the minimum service life for each structure type, which is 100 years for FRP and 75 years for concrete and steel. Our results show that an FRP wildlife overpass along US 97 using the composite tub girder is estimated to cost 11% more than the pre-stressed concrete bridge and 30% less than the steel girder bridge over 100 years, with the FRP overpass costing an estimated $346 per square foot, concrete is at $313 a square foot, and steel is $496 per square foot. The fencing element analysis follows a similar method as the girder analysis and compares FRP to wood and steel. This analysis assumes maintenance is equal between the three material types and focuses on the material and construction costs. The service life of the three materials are the main difference, being 35 years for wood, 50 years for steel, and 100 years for FRP. The table on the right shows the different mitigation element values used for this LCC. Our results show that using recycled plastic FRP for wildlife fencing, jump outs, and road access points along US 97 is estimated to cost 38% less than wood and 28% less than steel over 100 years. This averages out to about $36 per foot for FRP, $50 per foot for steel, and $59 per foot for wood. The initial cost of FRP for wildlife crossings may be higher than traditional materials, but are cheaper over time due to the low maintenance cost and a longer service life. An FRP wildlife overpass has maintenance costs estimated to be 50 to 80% less than steel and concrete equivalents. Using FRP for the girders of the wildlife overpass and fencing elements has an estimated life cycle cost about 5% less than using concrete and wood over 100 years, costing about $9.96 million for FRP compared to $10.45 million for traditional materials. FRP is a relatively new material and its ultimate potential is not fully understood, but our research has expanded this knowledge and has produced the following conclusions. FRP has a high strength to weight ratio and is extremely resistant to corrosion and environmental deterioration. FRP is an advanced and adaptive material that has limitless opportunities for transportation infrastructure. An FRP hybrid wildlife crossing and recycled plastic fencing elements can be designed and built along the US road network with minimal departure from DOT standard approval processes. FRP is economically competitive with other traditional materials used in wildlife crossings over the service life of the structure. Thank you very much for your time.